Section 7.2 is titled Powers of 10 and Scientific Notation. Hopefully you'll remember the majority of this from when you've covered scientific notation in the past. Our objectives for the lesson are that you can evaluate and multiply by powers of 10 and also be able to convert between standard notation and scientific notation. So first we want to talk about powers of 10. As we look at the powers of 10, 10 to the third, 10 squared, 10 to the first, 10 to the 0, 10 to the negative first, 10 to the negative second, and 10 to the negative third, you're essentially just dividing by 10 as we move from the left down to the right. If you're moving from right to left, you're essentially multiplying by 10. So each time you divide by 10, the exponent will decrease by 1, and the decimal point will move one place to the left. So let's take a look at that. We start from 10 to the third, and we move to 10 to the second. That's dividing by 10. So then notice how the decimal place moves one place to the left to give us 100. Same from 10 squared down to 10 to the first, that's another division by 10, and the decimal place is moving one place to the left to give us 10. Conversely, if you're moving from right to left, that's multiplying by 10. So here we have multiplication by 10, and notice that the decimal place that was behind the 10 is now moving one place to the right and giving us 100. Same thing from 10 squared to 10 to the third, that's multiplication by 10. So the decimal place was back here in 100, and now we're moving it one place to the right to give us 1,000. I would like you to have this chart written in your notes, as well as the 2 bullet points down below. So now let's just find the value of the number. 10 to the negative third. We can do this a couple of different ways. If you remember from yesterday's lesson, the previous lesson, that anytime you have a negative exponent, we need to move it down to the bottom and make it positive. This becomes 10 to the third. I think that using positive exponents when we're talking about powers of 10 is a little bit easier, because whatever the exponent is, that's how many zeros there are in that number. So 10 to the third is actually 1,000. So we have 1 over 1,000, or 1/1,000th. If we write that as a decimal, think about where the thousandth place is. It's the third spot after the decimal, and we get 0.001. So either answer here, 1 over 1,000 or 1/1,000th, both are acceptable. Number 2, we have 10 squared. Most of you know that 10 squared is 10 times 10, or 100. Next, we have 10 to the 0 power. Remember from the previous lesson that anything to the 0 power is 1. Now let's go the other way. Let's write each number as a power of 10. So we have 10 million. Remember, when we're talking about positive powers with 10, however many zeros there are, that's the power. So there are 7 zeros. This is 10 to the 7th. Number 5, we have 0.001, which if we write that as a fraction is 1 over 1,000. 1/1,000th is how number 5 is read. And we actually just did one like this before, but we can then write it as 1 over 10 to the third. But we don't want to keep our answer as a fraction. When we're writing powers of 10, we're writing 10 to a positive or a negative power, so 10 to the negative third. Something else that may help you with this, when we're dealing with the decimals, which means we're dealing with the negative exponents or the negative powers of 10, If you look at how many zeros there are after the decimal place, here we have 2 zeros. So your exponent then is going to be 1 greater, 3. But remember, because we're dealing with the decimal, it should be a -3. When we write just the number 10, it's like saying 10 to the first power. So that's how we would write it, as a power of 10. Scientific notation we use when we're writing really large or very small numbers, and it's written in the form a times 10 to the n, where n is an integer, so it's got to be a whole number, but it can be positive or negative. And a is either greater than or equal to 1, not either, it's greater than or equal to 1 and it's less than 10. So some examples of numbers written in scientific notation. We have 1.78 times 10 to the 15th, 5.3 times 10 to the -11th, and 1 times 10 to the 2nd power. Those numbers are all written in scientific notation, and we're going to talk about proper scientific notation. Remember, what's important is that n itself is an integer, and here's the other really important part. A must be greater than or equal to 1 and less than 10. And remember that A is the number, A is the number that's here in the front. So all of those numbers are between 1 and 10. So let's figure out if each number is written in proper scientific notation. You're checking, is the power an integer? And is the number in the front between 1 and 10? So number 7, we have 3.42 times 10 to the -7th. 3.42 does fall between 1 and 10, and -7 is an integer. So yes, this is written in proper scientific notation. Number 8, we have 52 times 10 to the 4th. Right away you should be noticing that 52 does not fall between 1 and 10. So this is not in proper scientific notation. When a number is not in proper scientific notation, we want to put it in proper scientific notation. So what we need to do is get that 52 to be between 1 and 10. So when we have 52, it's like saying 52, we put the decimal place in the back. We want to move that one spot to the left. We want to make it 5.2. But the number isn't 5.2 times 10 to the 4th anymore because we've moved the decimal place. So to compensate for making 52 smaller, 5.2 by 1 decimal place, we're going to make the exponent larger by 1 number. So when you have to move a decimal place in a number that's already in scientific notation, if you're making the number smaller, 52 down to 5.2 is smaller, then you want to make the exponent larger. And it will also work in the reverse case that we'll see here in number 9. So we have 0.004. No, this is not currently in proper scientific notation, but we can get it in proper scientific notation by moving the decimal place. Remember, we want this number to be between 1 and 10, so we're going to move it here and again there. So now we have 4. You can write 4.0, but you don't have to do that, times 10. And now we're going to go the opposite direction. We had 0.04 that we made larger, changed it to a 4. So we need to take the exponent and make it smaller. But be careful here because we're dealing with negatives. We moved the decimal place 2 places to the right, so we need to make -5. We need to decrease it by 2. Since we moved the decimal place 2 spots, we need to decrease this by 2 and get 4 times 10 to the -7th. Now it is written in proper scientific notation. So to write a number in scientific notation, we use a positive number to write a number that's greater than 10, and we're going to use a negative number or exponent to write a number between 0 and 1. The number comes from how many places the decimal point moved. You just have to remember, is it going to be positive or negative? So write each number in scientific notation. First you have to figure out where's the decimal. Well, right now it's back here. We need to move that decimal place so that we have a number between 1 and 10. So I need to move it all the way over between the 2 and the 6. That's going to give me 2.67. This number is between 1 and 10 times 10 to the, how many times did I move the decimal place? 1, 2, 3, 4, 5. 2.67 times 10 to the 5th. You try number 11 on your own. So the decimal place is back here. We're moving it 1, 2, 3, 4, 5, 6, 7 places to get us a number that is between 1 and 10. And so it's 10 to the 7th because we moved the decimal place 7 places. You need to make sure when you're writing scientific notation that you're bringing all the numbers along until you get to the repeating zeros. So I had to write all the way to the 5, but that's when I got to the repeating zeros, so I was able to stop. On number 10, I was able to stop after the 7. We don't have to write 2.67000. On number 11, you don't have to write 4.620500, okay? So you can leave off all those zeros that repeat at the end. Now let's go the other way. Now we're talking about really, really small numbers, so we're going to be dealing with negative exponents. But the same rules still apply. You still need a number between 1 and 10, and you still need the exponent to be however many times you move the decimal place. So the decimal's here. We're moving it 1, 2, 3, 4, 5 spots to get 3.25, but remember we're dealing with a small number, so it should be the negative 5th. We use the negative exponent when we're dealing with numbers between 1 and 0. This is between 0 and 1, so we use a negative exponent. Number 13, we're going to move the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9 spots to get 9 times 10 to the negative 9th. Now what happens when we go the other way? When we write a number in standard notation from scientific notation, the positive exponent indicates that the number is greater than 10, so you want to move the decimal to the right, and the negative exponent indicates a number between 0 and 1, so we're going to move the decimal to the left. Remember, positive exponents are very large numbers, negative exponents very small numbers. So now let's write each number in standard notation. We have 3.2 times 10 to the 7th. This is going to be a large number. The decimal place needs to move to the right, and it needs to move 7 places. So I like to write 3.2 out here on its own, and then move it 7 places. 1, 2, 3, 4, 5, 6, 7. And the question is, what do we fill in here? These get filled in with all zeros. But now we need to write the number properly using commas where they go. So this is 32 million. Number 15, we have 5.07 times 10 to the 4th, which means we're moving the decimal place 4 times. And we're moving it to the right again because we're dealing with a positive exponent, so we're dealing with a large number. So we move it 4 places, 1, 2, 3, 4. We fill in 2 zeros, and we get 50,700. Number 16, we start with 5.6, but notice the exponent is negative, which means now we need to move to the left because we're dealing with a number between 0 and 1. So we move 1, 2, 3, 4. We fill in with all zeros. And I would like you to put a leading 0 before the decimal place. So instead of just writing 0.00056, I'd like you to write that leading 0 out in front. That way you're sure not to miss that decimal point. It sticks out a little better when you put that leading 0 to the left of the decimal. Now let's look at an example where you're asked to order from least to greatest. This one's a little different because we've got numbers that are written in all different forms. And you'll see that the first number and the last number are not in proper scientific notation. And the third number is not in scientific notation at all. So when you're going to compare numbers, and some are in scientific notation, some are not, some are proper, some are not, the idea is to get all of the numbers into the same form. The easiest thing to do is to take them out of scientific notation. So if we start with number 17, we take it out of scientific notation, we're moving the decimal place. Notice that it's a positive 5, so we want to move the decimal place to the right. So we move it 5 spots, 1, 2, 3, 4, 5. We fill in any zeros, so this number is 630. We want to move this one 4 places, 1, 2, 3, 4, fill in any zeros. This becomes 60,300. The third number is already in standard notation, and the fourth number 3 places because it's positive, fill in some zeros, 63,100. Now we can compare the numbers. But what we also want to remember is that when we're ordering from least to greatest, we do want to write the numbers in the way that they appeared in the problem. So I'm not going to write 630. I'm going to write 0.0063 times 10 to the 5th. That's the least, that's the smallest number. Then we have 6,103. And be careful with your commas here so that they don't look like they're separating other numbers. And then we have the 60,300, so 6.03 times 10 to the 4th. And then finally, 63,100 was 63.1 times 10 to the 3rd. So these numbers are all written least to greatest. What I should point out is that sometimes it's common to assume that because a number has a larger exponent, it's actually bigger. And you can see that's definitely not the case here. Just because it was 10 to the 5th doesn't mean it was bigger than all the other numbers. And that's because it wasn't written in proper scientific notation. If numbers are written in proper scientific notation, then you can compare the exponents. The larger exponent would be the larger number, but these were not written in proper scientific notation. A couple more examples. We want to simplify but then write our answer in proper scientific notation. So when you're multiplying a number times another number in scientific notation, we just do 2.5 times 6. 2.5 times 6 is 15, and we copy times 10 to the 3rd. But it needs to be in proper scientific notation. 15 is not between 1 and 10, so if the decimal place is back here, we need to move it 1 to the left. That gives us 1.5 times 10. The question is, what do we do here? Well, we took 15 and we made it smaller. We changed it to 1.5. So we need to make our exponent bigger by 1. 1.5 times 10 to the 4th. Number 19, we have 0.4 times 2 times 10 to the negative 9th. So we do 0.4 times 2, and that gives us 0.8 times 10 to the negative 9th. And again, this number is not in proper scientific notation because 0.8 does not fall between 1 and 10. So we want to move the decimal place this time to the right to make it 8. And if we made our number larger, 0.8 to 8 is making it bigger. We want to make the exponent smaller. Careful, we're dealing with negatives. Negative 10 is smaller than negative 9. So these are your answers written in proper scientific notation. If we go back and look at the objectives, can you now evaluate and multiply by powers of 10? Take a look at examples 1 through 6. Do you have full understanding and comprehension of those 6 examples? Are you able to convert between standard notation and scientific notation? These were examples 10 through 19. So take a look at everything we've done there. If you have full comprehension, then you can answer yes. If you're still struggling with any of those examples, make sure you're asking questions in class. And we will work on worksheet 7 too.